Hi everybody, and welcome to Introductory Astrophysics, PHYS 320. My name is Professor Haggard, and I'll be your instructor for this term. We're going to give it a whirl with the remote teaching. I'm new to this, as I know many of you are too, so be patient and please send me and your TAs lots of feedback. We actually really genuinely do appreciate the information we get from all of you and the feedback we get from all of you. So please share it with us, and let's make it a great term. So a few caveats about the remote teaching. One is that I'll be at home and I have construction in my neighbor's house next door. So if you hear occasional banging or drilling, you'll know what that is. That has nothing to do with my well-being. Just bear with me, and hopefully it won't be too disruptive. I'm going to use this welcome video to tell you a little bit about the research that I do and a little bit about myself, and then we'll have a separate lecture that gets us started on the content for the term. So this is me. I'm Professor Haggard. This is my email and my web page. These are some of the best ways to reach me. Please also use our My Courses discussion areas. We really welcome discussion and discourse there, so please share your thoughts with us. Our class website will be offered through My Courses. Our textbook is Astrophysics in a Nutshell. The second edition is the one we're going to be using. It's been updated substantially since the first edition. So please try to use the second edition if at all possible. We will try to incorporate a few workarounds for all of you if you can only access the first edition. The McGill Library has an electronic version of the first edition available, so we can use that in a pinch, but please, if at all possible, get access to the second edition of Astrophysics in a Nutshell. It's a great text. I'm going to switch up the order a little bit, so that's a new experiment for this year, so that should be exciting. So we'll have lectures, these sorts of pre-recorded video lectures, about two-ish a week. They'll be between 20 and 40 minutes. And then we'll also meet via Zoom sessions at our regularly scheduled class time for question and answer and discussion. We'll recap some of the topics and talk about further derivations, run some examples, that sort of thing. So students who are outside of the Montreal time zone, please be aware that both of these are required. You do not have to participate in the Zoom sessions live. So please just feel free to join remotely. Send questions again through the discussion for us so that we can discuss them in those Zoom sessions even if you can't be there in person. It is not required that you attend any of the lectures this term live. It is required that you take all of those sessions as part of the content of the course. Take them seriously. Please watch them offline if you're not participating live. We'll go through the full syllabus on Thursday, our very first class meeting time, and so please tune into that. We'll go through the details of the grading, etc. Today I'm really mostly just saying hello and introducing you a little bit to myself. So my research group is the McGill Extreme Gravity and Accretion Group, so we call ourselves MEGA to be cute. Mostly we study black holes and neutron stars, sometimes other compact objects. Often we study the sort of explosive nature of these objects. So I work often at high energies using X-rays, gamma rays, etc. as a guide to finding the most sort of explosive events or the hottest, sort of most violent environments in the universe. I find this very exciting. I'm going to come to this in a minute, but in the image that you're seeing here on your screen, this is a beautiful multi-wavelength image of the galactic center. So this is the Milky Way galaxy. You're seeing right into the core of the Milky Way. Down here, where you can see this kind of bright swirl, is a very compact group of stars. I'll show you a video of those in a minute. And right down in the heart of that compact group of stars is a supermassive black hole called Sagittarius A star. So many members of my team study Sagittarius A star. We're also very interested in star formation. You can see all of this amazing structure. The bluer colors are marking out the higher energy or hotter material. The redder colors are marking out the lower energy or less hot material. And so this is really exquisite, beautiful data coming mostly from space observatories, our so-called great observatories launched by NASA in collaboration with the international community. So I'm also a member of the McGill Space Institute, and of course a faculty member here in the physics department. So Just to tell you a little bit about how I launched my own career into astronomy and astrophysics, I was probably a contemporary of many of you now. I was an undergraduate student in university. I was in a rather unusual degree program. I was actually studying philosophy, but we had lots of history of science and lots of scientific and mathematical courses in the course of my philosophy degree. And I was a junior, as they'd say in the States. I was in, I guess that would be equivalent to U2. And I was in a math class, and we were studying Newton's Principia. So we read only original texts, and my professor talked about how you could slingshot spacecraft off of the gravitational fields of objects in the solar system, and I was just blown away. I thought that was so cool, and you could do it, using the Newtonian mechanics that we were studying there in our classroom. So you can't fully see it here on this particular part of this beautiful poster, but these are all solar system missions, many of which do exactly that. So you can see these amazing swirls are marking out these gravitational assists or gravitational flybys that help propel spacecraft out into the solar system. So you can see here, these are two missions that got launched. You can see they go around, they get one gravitational assist at Venus, then they come around the Earth, and then they do a flyby and head out. So this one green line is Cassini. Some of you may have heard. They went and visited Saturn. The other one here is Galileo, which went and visited Jupiter. So this is a beautiful poster if any of you love this kind of thing. It actually goes all the way out and shows you gravitational assists out to Jupiter and to the more distant planets. So this is what got me inspired. It took me some time. I will talk at the very end of this very brief lecture about my career path, but I did eventually come back to astrophysics, and I've really enjoyed pursuing it as my research area. I'm super happy all of you are here starting your own explorations, and I hope you find the course exciting and fun the same way that I did when I was your peer in undergraduate. All right, so to talk a little bit more about what my research group does, I mentioned that supermassive black hole down in the heart of the Milky Way galaxy. We pet name that source, that black hole, Sagittarius A star. The reason for that is that if you were to look in the sky in the direction of the constellation Sagittarius, you would be looking straight toward the center of the Milky Way galaxy. And the supermassive black hole is actually embedded there in that galaxy. The A means it's the brightest radio source, the A star. So we use this often to denote the black hole that's in the center of a galaxy. You'll see me talk a little bit about M87. I might have forgotten the star on my slide, but in any case, Sagittarius A stars are sort of local supermassive black hole. My research group spends a lot of time thinking about Sagittarius A star. It's a very interesting source because it is a supermassive black hole very close by. It's 100 times closer than any other supermassive black hole to our vantage point here on the Earth. We also, because it's close by, we have had the ability and the techniques to actually go and to really trace out some of the material and the stars in the vicinity of the black hole. And just again, using Newtonian physics, we have had really great success in Keplerian physics, great success at measuring the mass of this black hole. So we know Sagittarius A star's mass and distance better than we typically would for a supermassive black hole. So this makes it a very interesting laboratory for studying dynamics, in particular in the context of strong gravity, so where GR is important. So when, as an observer, I'm an observational astrophysicist, when we go out and we look, we can detect Sagittarius A star, not the black hole itself, but the hot material around the black hole at radio and X-ray wavelengths, also submillimeter. And this radiation, we see variability, and my group often studies those variability characteristics, flares in the X-ray and the infrared. We don't see Sagittarius A star directly at optical wavelengths, and that's partly because we have to look from our position on Earth through the plane of the Milky Way galaxy, which is full of gas and dust, and that obscures our view at the optical and ultraviolet wavelengths. So we get, as I've mentioned, the mass of Sagittarius A star from the orbits, the Keplerian orbits of these massive stars that are in orbit around the black hole. I'll show you a video of that in 1 second. But my team really uses this sort of pursuit, this particular, it's not exactly a technique, but a sort of a strategy called multi-wavelength astrophysics. So the workhorse of many of my projects is the Chandra X-ray Observatory. This is one of those great observatories I mentioned. It's in orbit, actually out in a fairly long elliptical orbit around the Earth. And is one of the most elite, beautiful X-ray observatories. We get extremely good spatial resolution for our objects and really incredible information about the energetic universe. We also use ground-based observatories. Here you're seeing the Keck telescopes on Mauna Kea in Hawaii, and you'll see that they seem to be equipped with two very bright lasers. This is a technique called adaptive optics, a super neat technique where we basically create fake stars in the sky and then monitor their positions, and then we can see the wiggling. We can kind of correct out the wiggling of the atmosphere to get cleaner images using actuators on the back of the telescope mirrors. Very cool technique, very, 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 very significant for studying the stars and the stellar orbits in the galactic center. Last but not least, we also study at longer wavelengths the radio. This is the Very Large Array in New Mexico, and this is probing a different suite of sort of energies and emission. So the radio is also very important in this kind of multi-wavelength context in understanding supermassive black holes. The radio, actually I can point a little bit to it here. One of the things the radio is very excellent at is picking up synchrotron radiation. So this is radiation where electrons are spiraling along magnetic fields. And you can see in this artist's impression of a black hole, this jet that seems to be being launched very close to the position of the black hole and then has these twisting features which are magnetically controlled. And these magnetic fields with the electrons spiraling along them emit quite a bit of synchrotron radiation, which is detected at radio wavelengths. So you can see by using these different observatories, we can try to probe the hot photons, the material, the very hot gas in the X-ray. We can understand the larger environment by looking using adaptive optics at the infrared, and we can also use the radio to really probe these jets. So it's a very powerful strategy, but it is difficult to get all these observatories to work together in service to the science goals that we are excited about. All right, so I promised you a video of the stars around Sagittarius A star. So this is using those Keck observatories, those Keck telescopes that I just showed you a second ago. And you'll see these colored these little colored dots are actually stars. Those are showing you the profile, the radial profile of the emission from the stars. And you can see over the course of around 25 years now, we've been monitoring the positions of these stars. We can actually see them well enough to see their motions. This is very unusual in astrophysics. Normally things are too far away. It's way too hard for us to actually watch them move around like this. But in our own galactic center, as I mentioned, it's close by enough that we can actually monitor these beautiful stars and use Kepler's laws to figure out what the mass of the supermassive black hole is, Sagittarius A star, which is marked here just as a sort of a little indicator as a little white star. So in this image, in this depiction, Sag A star is too faint for us to pick out any of the emission near it. You're really just seeing the stars in orbit around what appears to be empty space. But you can tell that it's a very massive object there because it's controlling the orbits of these stars, really pulling them around in its gravitational field of influence. I mentioned also that at larger scales we study the accretion flow, that hot gas, and we see these flares. This is a beautiful example of X-ray flare coming from Sagittarius A star. Just to make it a tiny bit more confusing, because it's observational astrophysics, this persistent blue source you're seeing right here that my pointer is pointing to is actually not Sagittarius A star. That is a magnetic neutron star in the vicinity of the black hole. And then you can see just slightly off to the side here where the little white box is, that's the position of Sagittarius A star. And you can really see that booming bright flare when it goes into outburst. So my group spends a lot of time trying to understand what the mechanism is that drives these flares, where they are positioned with respect to the supermassive black hole, etc. And we are getting closer and closer to the event horizon. In particular, my group is a member of the Event Horizon Telescope collaboration, which all of you have probably heard about over the last few years because the EHT, as we affectionately call it, just recently released the first really spectacular image of a supermassive black hole. So we really, as we want to understand black holes, we really want to march down as close to that event horizon, as close to the surface of the black hole or the vicinity of the sort of sphere of influence of the black hole as we can. So the Event Horizon Telescope and the VLTI gravity instrument, which maybe you're less familiar with, are two instruments that are really the state of the art for getting a picture of the emission super close to the black hole. So you can see here the Event Horizon Telescope is actually a network of observatories that span the globe. These are observatories that observe at sub-millimeter wavelengths, which I didn't emphasize on my previous slides. The emission from Sag A star's accretion flow is actually maximal at sub-millimeter wavelengths, so this is a very good place to go if you want to try to take a picture of the supermassive black hole. This network of telescopes basically acts as one single observatory that gets a slightly different view as the Earth rotates, and they can get down to 50 micro arcseconds. So you might have read some of the press releases around their first announcement of an image of a black hole. They can actually resolve an object the size of an orange at the distance of the moon. So that's roughly kind of a metric for what 50 micro arcseconds might mean. So it's really, really amazing resolution, really amazing ability to pick out features that are extraordinarily small in the sky. So as I mentioned, the EHT operates at sub-millimeter wavelengths, and the VLTI gravity instrument, so this is the very large telescope, the VLT, down in Chile. These are 4 telescopes that this group, mostly based in Germany, has linked together. You can see these white lines are representing linkages. There are also a few little outrigger telescopes here. So the VLTI instrument gravity is actually using infrared wavelengths and doing the same thing, really trying to look and monitor Sagittarius A star and other really interesting AGN and other objects to understand what's happening, what is the dynamical structure of the emission very close to the black hole. They have successfully resolved some of those beautiful flares and helped us start to understand that flaring, I showed you that bright X-ray flare, we also see very bright flares in the infrared, and it looks as if that flaring is coming from a region very close to the black hole, about 6 to 9 gravitational radii. So that's a beautiful confirmation that flaring activity is actually a probe of the material close to the black hole rather than, say, an eddy out in the accretion flow or some other unrelated phenomenon. So the VLTI doesn't have quite the sort of micro arcsecond resolution. It's milli arcseconds, so you can see that their ability to resolve an angle on the sky is something more like 4 micro arcseconds, but still extraordinarily impressive. And together these two instruments can really help us start to probe those very small size scales near the black hole at 2 different wavelengths, which is extremely powerful in that multi-wavelength context I was describing earlier. All right, so of course you've all seen this amazing image. The Event Horizon Telescope released this first image in 2019 of a supermassive black hole, not Sagittarius A star. So I've talked about Sag A star a lot. That's my favorite supermassive black hole. But this is M87 star. So this is the really spectacular, very massive black hole that lives at the heart of the brightest galaxy in the Virgo cluster. So the Virgo cluster is a nearby cluster of galaxies, many galaxies gravitationally bound. Down at the center of that cluster is a brightest cluster galaxy, a very bright galaxy that contains this supermassive black hole at its heart, at its core. M87 star is much more massive than Sagittarius A star, about 100 times more massive, and is further away. So the interesting thing is that its larger mass implies a slightly larger physical footprint on the sky, but its distance makes that footprint smaller, right? As you move something further away, it looks smaller and smaller from the perspective of the observer. So it turns out that M87 star and Sagittarius A star are roughly the same physical size, the same angular size on the sky from the perspective of the Earth observer, for example, all of us using the Event Horizon Telescope. So M87 star and Sagittarius A star are these 2 really exciting supermassive black holes where we have the opportunity to study them in about the same kind of detail, even though they are, as I said, about 100 times different in mass. So to zoom out a little bit and show you the larger context of this beautiful galaxy that this amazing supermassive black hole lives in, this is an X-ray image, again using the Chandra X-ray Observatory, looking now out at the larger scales. And you can see one of the impressive things, this is even more impressive if I were to show you a radio image, which I will in a future lecture, but M87 actually drives an extraordinarily strong and magnificent jet. So this is that jet. We've zoomed in a little bit here on the core of the galaxy. It has a very strong jet, one of those magnetic structures that I mentioned. This is very bright in the radio as well. And you can see there's also tons of hot X-ray gas. So X-ray gas is typically millions to billions of degrees Kelvin. So you're looking at this like incredibly hot environment and really buried way down, deep, deep, deep inside, down at the core here, right at the base of this jet. Is this gorgeous supermassive black hole. So this is the power of multi-wavelength astronomy. We can probe different size scales, we can look at different dynamics, we can try to understand what's going on, how mass is getting into the black hole, how the black hole is driving mass back out. and how all of those phenomena are interacting with this larger galaxy. So this is very exciting. I'm extremely thrilled to be a part of the EHT collaboration, and we're very close to being able to share results about Sagittarius A star here in the Milky Way galaxy. So just hang on. I'm not sure it'll happen this term, but maybe I'll sprinkle little teasers in as we go along this term, but sometime within the next year. All right, so my group also works on a different domain. So now when we come to talking about black holes, I'll describe this a little bit more, but they break into two classes: supermassive black holes and stellar mass black holes. So a stellar mass black hole is something like 10, maybe 100, maybe 1,000 times the mass of our own sun, while a supermassive black hole is 1,000,000 to 1,000,000,000 times the mass of our sun. So they separate into these two categories. There's not much in between, which is kind of a remaining mystery in astrophysics. But leaving that mystery aside for now and just focusing on these low mass ones, we've just recently entered this era where we can look at or observe stellar mass black holes using their gravitational radiation. So when you have two black holes together, they spiral around and they kind of whip up the fabric of space-time, and send out gravitational waves, which propagate at the speed of light, but that are in fact an undulation in the fabric of space-time rather than an electromagnetic photon, which is the thing we normally look at as an astronomer anyway. So the LIGO experiment coupled together with Virgo have been detecting gravitational waves since 2015, but in 2017, we had our very first detection both of an object both at gravitational radiation and in electromagnetic radiation. Turns out this was not two black holes merging together. This was a black hole and a neutron star it was two neutron stars experiencing this in-spiral and eventually a collision and an explosion. And this neutron star merger created a kilonova, basically something like a smaller supernova explosion, which we were able to detect with telescopes. So this is a beautiful image of the galaxy in which this collision occurred. The white box is showing you the neutron star merger, where the two neutron stars smash into one another and create this explosion. So this is the really spectacular event known as GW 170817. My group was very excited to lead some of the X-ray observations, which you're seeing. This is fading from a Hubble Space Telescope image into a Chandra X-ray Observatory image, so fading from the optical UV into the X-ray. And my team was one of the teams that led these X-ray observations. We were very excited to be a part of this discovery. Why do we care about neutron stars merging together in space? So it's super cool, obviously, but the other reason that it's fascinating is that when you merge together two neutron stars, you undergo a lot of nuclear reactions called rapid process reactions, where you're feeding neutrons into these very high energy shocks and other things very quickly, which allows you to build up very heavy elements. And we think that, in fact, these neutron star mergers are a major player in creating some of the heaviest elements at the bottom of the periodic table. So we'll talk about this again more as well, but these neutron star mergers actually might play an important role in creating metals, fancy things like gold, like wedding rings and platinum, but many other important elements that sort of reside in that heavier R process element portion of the periodic table. So my team, as I mentioned, was one of the early teams to observe this event. These are some models. We saw the collision initially. We didn't see anything in the X-ray. About a week later, we first started to see this shocking outflow coming from the merger of the two sources of the two neutron stars, and it rose slowly over time. There was a period where the sun was too close to the observatory. We couldn't see anything. We were blinded by the sun. So, and then we saw it rise over time and then decay over several years' time, actually. So this is really amazing to have seen these two neutron stars, to have detected them in gravitational waves, to have followed them up across an entire huge range of the electromagnetic spectrum. So this was a spectacular and very exciting discovery. There was lots of debate about why this emission evolved in the way it did, and we've started to learn a lot more about how neutron star mergers not only create elements in the periodic table, but also drive outflows and shocked gas that smashes into the medium in the galaxy in which the neutron stars are living. So this is very exciting. This is known as multi-messenger astrophysics. I have an entire part of my team that works on multi-messenger astrophysics, looking for mergers of neutron stars, but also mergers of black holes with neutron stars, where the black hole might shred the neutron star up before the neutron star is kind of completely gobbled up by the black hole. And so this is a fun and very exciting new discovery discovery area. All right, so I said, just to wrap up, I'll tell you a little bit more about my background and myself. I'm originally from New Mexico. This is my great state down in the southern part of the United States along the Mexican border. This is our New Mexican flag. So I was raised there. I was actually born in Seattle, Washington, but raised entirely in New Mexico. So I hark from down south. My educational background, as I mentioned earlier on, was actually in my undergraduate degree was in philosophy at a rather esoteric institution called St. John's College, a really fantastic classics or great books program. I loved it. It was fantastic. It wasn't what I was planning. I thought I was going to go into science even early on, but I kind of deviated into philosophy for a little while and then found my way back to physics. I did a master's degree at San Francisco State University in physics, and then I moved to the University of Washington. I returned to my birthplace, Seattle, and did my PhD, a second master's degree in my PhD there, under the supervision of Scott Anderson. So I worked on active galactic nuclei, which are growing supermassive black holes. So professionally, I have been here at McGill for about 5 years. I'm an associate professor in the physics department. Prior to that, I spent a year on the faculty at a liberal arts college called Amherst College in Massachusetts. And I was also a postdoctoral fellow at Northwestern University just outside of Chicago. So I talked to a few students about what is a postdoctoral fellow? So this is a period between when you get your PhD and when you pursue maybe a faculty position or another kind of career path where you're just purely doing research. So you are no longer in your sort of student mode, but you're now really a fully independent researcher driving your own projects. It's a very exciting time and it's fun, and you don't have teaching or other service responsibilities, so you can really focus wholly on doing research. So that's often a very productive, very interesting, research-intensive time for scientists. For me personally, that was the first time I started working on the Galactic Center in Sagittarius A star. So my time as a postdoctoral fellow really drove a lot of or continues to drive a lot of the science I do today. I also have spent a lot of my time doing outreach and mentoring over the years. I've been a part of NSF programs that placed graduate students in the public schools to work on developing curricula and working with students in underprivileged neighborhoods. While I was at the University of Washington, I also worked on a very fun program called PreMap, which took incoming students and introduced them to research very early in their academic careers to help create more continuity and research engagement along the way. I'm still very excited about working with undergrads for research. I think some of the members of this class are actually joining my research group this fall. So that's really a great pleasure, and I hope you all will seek out those opportunities because it does, I think, really enrich your education to do research projects. I also have had moments in my career where I was not in academia. So as I said, I did a degree in philosophy, and then for a while I actually worked outside of academia entirely. I spent a year living in China and working there. And then I also spent several years working in Silicon Valley. I was a full-on marketing person in Silicon Valley in the late 90s, so right around the dot-com boom. I wore a suit to work every day and had a very sort of much more corporate life. So if anybody is interested in talking about career paths, I'm always happy to have those discussions as well. Mine has been winding, much like those gravitational slingshotting experiments in the solar system. So I also spend quite a bit of my time thinking about issues surrounding diversity, equity, and inclusion in STEM. I care deeply about this. I've worked on it for a lot of years. And I think all of you have probably seen the world rather galvanized around the murder of George Floyd and all of the Black Lives Matter movement. So I think these are interesting discussions to try to bring home and really hold also in our department and our spaces as professors and as students. So I am very engaged in this kind of work, and I'm always happy to talk about it as well. We can set aside time. It shouldn't be part of our class time, but it is a part of my academic world. I'm a member of the Equity, Inclusion, and Diversity Committee for the Canadian Astronomical Society. I have participated in the Committee for Women and on various different important task forces for the American Astronomical Society, which is based out of the US. I've also been a part of our Women in Physics and EDI committees here at McGill and previously at Amherst. I also try, and I hope all of you will too, to do a fair amount of self-study to help me understand the history of racism and sexual harassment and other things, not only in STEM, but in our communities more broadly, in which all of our science is embedded. So invite you to do some of that work yourselves and to learn a little bit more about it. I do think it will enrich your life and your experience in your communities, and it also is very important in our own communities in our classrooms. And last but not least, I spend really most of my professional life doing research and teaching and working with all of you. I have about 65 refereed publications. This means they've been through a peer review process. They have thousands of citations, and someday you'll learn about an H-index. It's not that exciting, but any of you who pursue academia will eventually learn that you have to be a little bit beholden to these metrics as well. I write tons of grant proposals and telescope proposals. As I've emphasized, I'm an observational astronomer, so I spend quite a bit of my time trying to compete for and bring in new data for my team to work with and to help us kind of try to pursue some of these exciting questions about neutron stars and black holes. I also write tons of funding proposals in order to fund my work and the work of my collaborators, and so that's been pretty successful, and you'll sometimes hear me say "mer mer mer" about some grant proposal I have to do, but it's actually a pretty fun part of my job, but it does take a fair amount of time. So thank you all for listening in. It's really lovely to introduce myself to you. Hopefully I'll get to meet all of you in our Zoom sessions, and I'm very much looking forward to this fall term, and I hope that it's as rewarding for you all as I anticipate it will be for me.